This SAP 2000 tutorial will show how to use fast nonlinear analysis, or FNA, to analyze a model with dampers and base isolators. Fast nonlinear analysis allows for extremely efficient and fast nonlinear analysis when nonlinear behavior is limited to predefined locations. The FNA analytical technique lends itself extremely well to modern earthquake design practice, where the goal is to restrict the nonlinear behavior to very specific regions of the structure in an effort to minimize overall damage, analogous to the job of a fuse in an electrical circuit. Thus, items such as dampers and isolators are easily modeled using the FNA technique. What is fast nonlinear analysis? FNA is nonlinear modal time history analysis using load-dependent Ritz vectors. We start with 3 moment frames. The frames are identical except that the frame on the right has a crossbeam at its base, which we will explain shortly. The first frame will not be altered. It will serve as our point of reference for the other 2 frames. The middle frame will have diagonal viscous dampers, and the last frame will rest on friction pendulum isolators. The bottom beam is needed to tie together the column bases. All 3 frames will be subjected to the same earthquake ground motion. We start by defining the link properties that will be used to model the dampers and isolators, which is done under the Define Section Properties Link Support Properties command. Here we will add a new property of type damper exponential. Which we will name damper. It will have properties in only the local U1 direction, which is along its axis. It will be a nonlinear element, and if we click the Modify button, we can specify its nonlinear stiffness and damping properties. The values we are specifying here are somewhat arbitrary and will typically be dependent upon the structure, the damper characteristics, and the desired amount of energy to be dissipated. However, it is important to use an appropriate stiffness, as too large a stiffness may result in significantly unconservative behavior. Next, we will add an isolator property. We will use a type of triple pendulum isolator. Which we will name isolator. This object will have properties in 3 directions: U1, which is vertical, U2, which is horizontal, and R3. U1 will have an arbitrarily large stiffness for the vertical springs. R3, the rotation stiffness, will also be relatively large. The U2, or horizontal direction, is where the nonlinear pendulum properties will be specified. The pendulum might look somewhat similar to this. It has up to 3 radii that can be specified for the sliding surfaces, which defines the behavior of the 3 pendulums. We will uncheck the outer bottom surface is symmetric to outer top surface, as we will specify 3 different properties. The values shown here are somewhat arbitrary, and again would be determined based on the properties of the structure being isolated and in conjunction with the isolator manufacturer. With our isolator and damper properties defined, the next step is to add them into the model. Go to the Draw Two-Joint Link command and make sure that the property of damper is selected. Draw the damper objects as diagonals at each level of the middle frame. Click on the Select button to leave the Draw mode. Now, click the Draw One-Joint Link command to add the isolators. Select Isolator and click at the bottom joint of each column in the right side frame. Again, click the Select button to leave the Draw mode. Next, we will define the time history input. We will use a function from a file, in this case an El Centro earthquake. This particular file is in a time and function value form with 3 data pairs per line. We will also add a ramp function for applying the dead load, which we will call ramp. The slope of the ramp will be 10 seconds in length. Let's explain why we need to define a ramp function. The base isolators are friction pendulums, and thus their behavior is controlled by friction forces, which means that the isolators must be loaded with the vertical load before the earthquake analysis begins. Thus, we need to define the dead load using a time history. In this case, we use a function that slowly ramps up the load in combination with high damping to approximate a static load. Now we will define our load cases. We have 2 default load cases, dead and a modal case, both of which we will modify. For the modal case, we will change the name and the mode type to RITS. In order to perform FNA, load-dependent RITS vectors must be used. We will ask for a total of 40 modes. We need at least 20 for the 3 3-story frames, the 3 dampers, the 2 isolators, and the dead load, but we'll ask for 40 to be safe. For RITS modes, we need to define the starting load vectors. In this case, we will use acceleration in the x direction, the dead load pattern, and the built-in deformation load for the links. Next, we will modify the dead load case so that it is applied dynamically rather than statically. This will be done as a nonlinear time history using RITS vectors. This is FNA. The fast nonlinear analysis is a nonlinear modal time history using the Ritz vectors. The load applied will be the dead load pattern using the ramp function. For the ramp loading, we will use 20 time steps at 1 second each, and will increase the modal damping to 0.999. We are looking to slowly apply the dead load so that dynamic behavior is not excited. We will also add a new load case for the nonlinear time history, which we will call FNA. Again, the fast nonlinear analysis is a nonlinear modal time history using the Ritz vectors. For this load case, we will start from the conclusion of the dead load case. The loading will be the El Centro acceleration record, scaled from G units to inch units. We will use 5,000 time steps at a step of 0.002 seconds for a total of 10 seconds. We will leave the modal damping constant at 5%. No other changes will be made. We will now start the analysis. The nonlinear analysis is already complete. Now, we will display the FNA earthquake deformed shapes. At a time of 1.5 seconds. We can see the deformation of the 3 frames at this time step. Next, we are going to create a plot of the input ground acceleration. We will save it as a named set, ground Excel. The best way to see the dynamic behavior is to create a video of the time history response. We will create the video using the FNA earthquake load case for a time span of 10 seconds. We will also ask that the previously defined ground acceleration graph be displayed, and will increase the magnification factor to 20 so that the deformations appear larger and easier to see. Let's see this once more. The visual behavior of the dampers and isolators is as we expected. As a last check, we will review plots of displacement and acceleration for the 3 frames. We will plot output at joints 8, 16, and 24, which are the top corners of the 3 frames. Returning to the Show Plot Functions command, we will select the Joint Displacement Forces option. And starting with joint 8, we will select displacement in the X direction. We repeat this for the other 2 joints. We will switch the color for joint 8 to make it easier to see. Note that the smaller displacement pattern occurs at joint 16, which is the damped frame, and the largest at joint 24, which is the base isolated frame. This is as we would expect. Now we will look at accelerations. We simply modify each plot function to display absolute acceleration. This time, the moment frame has the larger acceleration pattern, while the isolated frame has the lowest, again as expected. This concludes this example on using the fast nonlinear analysis technique for rapid and efficient nonlinear modeling.